Hi, my name is Augusto Partida, and I will be reviewing the research paper Detecting Near Duplicates for Web Crawling by Manku, Jain, and Das Sarma, who were Google employees at the time when they presented this paper at the proceedings of the 16th International Conference on the World Wide Web in May 2007. So first, let's give a bit of background. A search engine is made of many components. We are only going to highlight a few. The authors of the paper define the scope of their research in the context of a search engine. The web crawler retrieves websites and mine information from the internet and traverses the search space by following the outgoing links of a website. The indexer generates a repository that is organized and structured for retrieval of relevant data that has been crawled. The search component is triggered by the user at the display component to parse the input query and correlate similar data that has been processed by the indexer. The display provides a rich experience for the user and lists the results gathered by the search component. For this research paper, we need to focus on the performance of the web crawler. The web crawler is a software component that takes as input a whitelist and a blacklist. The whitelist is a set of approved websites that allow the web crawler to mine its information. On the other hand, the blacklist is not okay with being mined, so we will be polite and leave them alone, as discussed in the lecture. We can think of the web crawler as generating a graph of the internet where incoming and outgoing links are edges and websites are nodes. In the world of data structures and algorithms, this is an adjacency list. As you can gather, this dataset will be extremely large. For context, the Common Core project crawled 99 terabytes of data in December 2023 alone, with petabytes of data over the span of a few years. So, what are near duplicate websites, and why are they important to be identified in the context of web crawling? Two documents are considered to be identical or near identical if they differ by at most a variable in terms of content. The authors don't consider advertisements, counters, nor timestamps as they are irrelevant for web search, as was discussed in the lecture. This is assuming that the search engine is focused on providing results that are not this type of content, such as Google, Bing, Yahoo, etc. It is important to identify near duplicates in order for the web crawler to choose to 1. Ignore the duplicate, which saves space, and also leads to reduced storage, which for a business may mean reduced hardware cost. It could also ignore the duplicate's outgoing links, which saves the search space. This leads to reduced network bandwidth. Also, this improves the quality of search indexes because it removes redundancy, which leads to better quality indexing for the search engine, as the user does not have to filter through duplicate results for their data. The research goals identified by the authors are 1. To develop a near duplicate detection system for large website repositories, where the latent goal is to improve the Google search engine to provide fast and meaningful results online. This means that a brute force approach would not work. The next goal is to demonstrate Sharakar's fingerprinting technique is appropriate for the task at hand. This is crucial, as the large website dataset that is crawled needs to be piecewise featurized, as discussed in the lecture. Third, they present an algorithmic technique for identifying near duplicates given a search query and a constant number of differences. This is called the Hamming distance problem, and it has been studied previously by Marvin Minsky, amongst others. The authors contribute to the solution by providing a novel algorithm that processes queries online without having to restructure the search space. The challenges for a near duplicate detection system are 1. Scale. Search engines index billions of web pages. This amounts to multi-terabyte databases with heterogeneous information that need to be updated with new data continuously. As described in the lecture, the priority should be given to data that has not been seen previously. The next challenge is processing. The web crawler can crawl billions of web pages per day. Thus, the near duplicate detection system needs to be able to identify a near duplicate quickly, without being a bottleneck to the web crawler. Finally, resources. The authors chose to implement a localized approach to identifying near duplicate web pages in order to minimize latency by keeping as few machines as possible. This means that the authors chose to solve the problem of detecting near duplicates by design instead of hardware. One of the research goals is to show that Sharakar's same hash technique is useful for the task of creating a near duplicate detection system. The authors chose to use same hash over shingles, min-hash, and information retrieval techniques due to its performance and dimensionality reduction. The power of SimHash is in its ability to map high-dimensional vectors to small-sized fingerprints. In the context of web crawling, this means featurizing website content into a vector with an optional weight for each feature. Through experimentation, the authors arrived at 64-bit fingerprints to represent the reduced dimension space for detecting near duplicates of an 8 billion web page content repository. Going forward, it is worth noting two properties of Shahrikhar's SIMHASH technique that he proved in his seminal paper in May 2002. The first is that the fingerprint of a document is the hash of its features. This means that the Hamming distance may be used to compare hashed feature vectors. The second is that similar documents have similar hash values. This is an example of a locality-sensitive hashing scheme. This means that the triangle inequality holds, and so do the properties of clustering. This is important since clustering similar objects is analogous to identifying near duplicates. Briefly, the procedure to generate a fingerprint for a web document using Shahrikhar's SIMHASH is to first featureize the words in a document into a vector as shown in the input row. This may include an optional weight for each feature that can be used to signify the importance of one feature over another. Next, each feature is hashed into a 64-bit fingerprint. Finally, for each hashed feature, we compute the 64-bit fingerprint for the document by computing the weighted sum for each column bit and verifying that the result is less than or greater than 0. Note, this follows the procedure mentioned in lecture for distance measures and featureization. Another research goal is to provide a solution to the Hamming distance problem of identifying whether an existing query differs from a search query by a constant value. The authors used precision and recall to experimentally compute a value of 3 bits difference for identifying near duplicates for documents with a 64-bit fingerprint. Again, the search space for this research is a repository with 8 billion SIMHASH fingerprints. To search for near duplicate websites of a given document, the authors explored the infeasibility of a brute force approach. As covered in lecture, this entails sorting the repository of fingerprints and conducting a binary search for the nearest matches, provided that they are within the threshold of 3 bits Hamming distance from the query document. The issue with this approach is the search space is combinatorial for each query, given the length of the 64-bit fingerprints and the 3-bit threshold. Instead, the authors provided an online approach where they took advantage of the bit structure for similar document fingerprints. They noticed that for duplicates and near duplicates, the most significant bits rarely changed, with the least significant having the most differences. This provides an approach whereby the fingerprints may be spliced into tables or buckets and searched more efficiently in the order of linear time given the length of the fingerprint. The first step to process search queries online is to generate a fixed number of tables from the repository of document fingerprints. The authors experimented with the number of tables ranging from 4 to 20. This in turn split the 64-bit fingerprints into blocks of fixed width. For example, if the number of tables is 4, then the 64-bit fingerprints would be split into 16-bit blocks. The tables are then permuted to allow each block or blocks, based on the design, to be the most significant bits in the search space. It should be noted that the authors provide a general solution for the most optimal number of tables, but we won't go over that here. Finally, a search query is able to be processed in cascading fashion by comparing the top most significant bits that are within the Hamming distance threshold, then following the next block in its chain until all near duplicates are found. The power of this approach is that since near duplicates will cluster, the near duplicate detection system is able to process the search query in parallel. To summarize, the general algorithm for detecting near duplicates follows the template exemplified in the lecture. First, we featureize the contents of the document into a vector by removing stop words, punctuation, or optionally compute a weight for each vector. Then we SIMHASH the feature vector, we execute the online algorithm to find potential near duplicates, and then we update the SIMHASH tables to include our query since we want to learn from previous experiences. Finally, we allow the web crawler to execute some sort of action based on the near duplicate. Why should we care about detecting near duplicates? The answer is that searching for data has become ubiquitous in our everyday lives. We rely on search engines to provide data that is meaningful without noise or clutter in the results. The authors identified that overall, their research goals were to improve web crawling, which in turn improved the indexing of websites and results provided to the user. As discussed in lecture, this entails identifying sources of duplicates and near duplicates such as web mirrors. This system may also be used for clustering related documents based on topic, region, or other similarity factors. Data extraction is also possible with the system, as one could envision using the metadata that was ignored, as mentioned before, to extract structural similarity. Outside of web crawling, the near duplicate detection system may be used to identify documents that have been plagiarized or copyright infringed. Spam detection is also important as the clutter it provides is an issue we deal with daily. This paper has more pros than cons. Specifically, the system was designed to be extensible, as it is still in use to this day. The richness of the paper cannot be understated. By coalescing the SIMHASH technique and providing a novel approach to an existing search problem at scale, the authors extending the application of their system. For example, the design decision to allow for parallel search fits into adapting MapReduce for parallel processing of search queries in batch. The authors also had foresight by presenting a series of questions for future enhancements ranging from categorization of web pages to whether it's possible to detect near duplicates regardless of redundant data such as advertisements. The only con is that it is too short and does not provide details for some of the claims, which are left to the reader to research. Thank you for listening to my review of this paper.